welcome folks. So in this class we will study resonance in LCR circuit. Okay, now for this let's draw a quick series LCR circuit. Okay, now in this we have already studied the case where VL is greater than VC, and this is LC and this is a normal reactor resistor, and we have studied the first case VL greater than VC and XL is greater than XC. Second case we have studied VC is greater than VL and XC is greater than XL. Okay, and third case VL is equal to VC and XL is equal to XC. So basically here what happens is only resistance comes into play. Now if I draw the phasor diagram, everyone knows the phasor diagram is like this, and this is VR, this is VL, correct, and this is VC. Okay, and you know it, right, that VL and VR are perpendicular, and same VR and VC are perpendicular as well. These are all peak values or RMS value. Okay, also this can be represented in this way, as like XL, XC and R. So in the third case what happens is this is equal to this is equal to this. However, so only the the values remain the same, because the direction, of course, VL would be more than VR by 90 degree, and VC would be lagging behind by 90 degree. So that would remain the same, but the peak values will remain same in the case of resonance. In the last case when VL is equal to VC and XL is equal to XC. So this would be net, the impact would be what? R, and it would be impedance. Here you will get impedance, this would be impedance. Okay, in this case this and this cancels, so the net is in this direction, and which is the direction of current as well. Now we have to note down one more thing here, that in this situation, the third situation, we can write Z is equal to under root R square plus XL and difference of XC whole square. This is R. Okay, now that means at Z is equal to R, it is minimum value of impedance. Minimum, if I put it this way, minimum value of impedance. So by this formula, so we can say that the minimum value of this would be when this would be 0, correct? That is XL is equal to XC. So this is the minimum value of impedance. However, you have to note down one more thing, that I naught, that, or let me put it here, I naught is equal to V naught by Z. So when this is minimum, this would be maximum. Okay, so the peak current would be maximum, when we are at resonance state, or VL is equal to VC, or XL is equal to XC. Okay. So in other words, I can say, about the resonances. For example, you are tuning in LCR, and the moment VL and VC becomes equal, or XL becomes equal to XC, all of a sudden the effect of this and this actually cancels, and this becomes a pure resistive circuit, and all of a sudden the peak current becomes the maximum. So I can say purely you know purely resistive circuit, purely resistive circuit. And you know uh, at this point the phase difference, of course, of in the purely resistive circuit, the phase difference is, what is the phase difference, is zero, because 10 phi is equal to x, you know xl minus xc by r. So this becomes zero, so phase difference becomes zero. Okay, so this is about the resistive circuit. We covered a bit when in the earlier lectures as well, but because here we are talking about the case number 3, which is when VL is equal to VC, XL is equal to XC, and at this state, the circuit behaves as a purely resistive circuit, because XL is equal to XC, and in the purely resistive circuit, if the current is, let's say, I is equal to I naught sine omega t, then this becomes, this is of course in the same phase, so V is equal to V naught sine omega t. Why? Because there is no that it behaves as a pure resistive circuit, so there are no effect because of inductance and capacitance. Okay, now, as we just said, if XL is equal to XC, so I can say omega L, omega naught L is equal to 1 by omega naught C, correct? Or I can say omega naught is equal to 1 by under root LC, correct? Or I can say, what is omega naught? It is nothing but 2 pi F0 is equal to 1 by under root LC, okay? Or this we can say F is equal to 1 by 2 pi under root LC. Okay. Now, most important is not the derivation, but to understand what exactly is the resonance and what happens when there is a resonance in LCR circuit. So you need to understand the theory which I have just given here, and then of course the derivation of this formula, which is pretty easy, but understanding is more conceptual. So we got this formula. This is called as resonant frequency. Okay. Now let's talk about a few graphs. So if you see the graphs here, and we know that XL is equal to omega L, which is 2 pi FL, and XC is equal to 1 by omega C is equal to 1 by 2 pi FC, correct? Now if I draw the graph, right? If I draw the graph, so first XL, this is resistor is of course for resistance, it is straight. So let's trust it. Let's come one by one. Now, if I talk about XL, see, it is both are linear. XL, this is linear because both are directly proportional. So it will be what? Something like this. Let's say, yeah, it's something like this. Now, if I talk about XC, this is, by the way, this is frequency and this is resistance, right? Frequency, resistance. So now if I draw the third one, which is XC, it is XC is this, XL is this, and this point is FO, frequency, correct? So let me again tell you, see, we know XL is equal to omega L, XC is equal to 1 by omega C. Now we are drawing a curve between resist R and F. Okay, now for R it is a straight line, correct? Okay, for XL we know, this is directly proportional to this, correct? So it will be a slant line with angle of what? 45 degree, correct? And XC is equal to 1 by omega C. It is this shape. Okay. Now, if we draw a graph with, let's say Z versus F, Z versus F. Now, in this case, remember, let's say it's something like this. This is F and this is Z. Z. Okay. Now, if you realize this, that Z is equal to what? R square plus XC minus XL whole square, right? Or if I put the values, I can say it is what? R square plus 2 pi FL minus 1 by 2 pi FC and whole square. Let me make, yeah. Okay, so Z is equal to under root R square plus XL XC or minus XL whole square, or after putting the values, I can say it is 2 pi FL minus 2 pi FC. Now, one thing you have to note down here. See, in this case, if F becomes small, let's say this becomes small. So if it becomes small, what happens is this will become, let's say it becomes very close to F. Let's say if F becomes small. If F becomes small, then this becomes towards 0, but this goes infinity because it's 1 pi, right? So this whole becomes too much, correct? Okay, so Z becomes large. I can say Z is large. On the other hand, if F is large, if F is large, then this is high and this is low. So the bottom line is the curve of this would be something like this, and at that point somewhere it would be the minimum value. So at that frequency, Z would be minimum and will be equal to R. Okay? Okay. Now, okay. Now, if I modify it a bit, let's say I draw a curve between, let's say between F and I naught. I naught. So we know this formula, right? We know I naught is equal to V naught by Z. Okay, so that means, when Z is high, I naught is low. Correct? So it will start from here. Now, in the second case, And when the frequency would be high, would be somewhere in the middle, right? See, basically what is happening is it will come like this, and then I will explain it to you. F naught, this is F, and this is somewhere in between. So now try to understand. See, when frequency is low, you know, if you see this formula, if you look at this formula, I naught is equal to V naught by Z. Now, when when I naught, see, I naught can be low at both the cases when Z is very high. Now, when will Z be high? I told you two cases, this and this. So, in both the cases, I naught would be low. Now, somewhere in between, I naught would be high, where when XC is equal to XL and both cancels each other, and it's a pure resistive circuit. I hope it is clear now.